Yay!
Yay! Hey, what's up? This is our first example dealing with some sort of accelerated motion in sort of an accelerated, where an object is in an accelerated frame. So let's dig in and see what you're supposed to do. The standard kind of simplest example that we'll tackle first is a person on an elevator. So suppose you got a person, and what we're going to do is stand the person on a scale. So maybe that is my scale that's going to read the weight in newtons. And what we're going to do is we're going to call this the apparent weight, because it could change. You imagine if you're in an elevator and it's going down, when it starts going down, when it accelerates downward, you feel a little bit lighter, right? And when it accelerates upward, you feel a little bit heavier just for a moment. So that's sort of your apparent weight, because the force of gravity from the Earth hasn't changed, of course, because it only has to do with you and the Earth, but the apparent weight has to do with the acceleration. So what we're going to say is, and if you think about it a little bit, maybe it's obvious, the apparent weight is going to be what we've been calling the normal force, right? That kind of makes sense. The normal force is the force of contact between two surfaces. In this case, it'll be the force of contact between you and the scale. So if there's more forceful contact between you and the scale would read heavier. You weigh more. So that's what we're going to do. All right. So let's say that this elevator is accelerating downwards at 4 meters per second squared. And what we want to do is find out what your reading on the scale is. So we apply Newton's second law, as always. And the idea is we're going to sum the forces. These are vectors, right? And again, I'm going to try to say it carefully. If I sum the forces together, they will equal the mass times how you are accelerating, how the thing is accelerating. All right, in this case, we only really have to worry about the y direction. Nothing really is happening in the x direction. So in the y direction, what have I got? Well, I got that normal force. Really, it should come from the scale, right? But anyway, it's pointed up, and pointed down, I have mg. Let's say our standard person is going to be 100 kilograms. That's a nice round number. Those are the only two forces involved, right? So I've got my normal force positive minus mg is negative. Those are the only two forces. So I add them together, and then this has to equal the mass times how this thing is accelerating. Well, we know how it's accelerating. It's accelerating in the down direction, right? So I have to be a little bit careful. And in fact, let me go ahead and just to make the point, I'll erase it and make this minus ma. A is in the same direction as mg, which I've called down. All right, so now I can do it. Now my normal force is mg minus ma. Before I plug the numbers in, I mean, just look at this for a second. Mg is sort of your regular weight. Right? If you're just standing on a scale, it would read mg, if you're motionless in a room, or constant velocity. Anyway, if you're not accelerating, right? We'll get to all that later. Anyway, mg is just sort of your regular weight on a horizontal surface. ma, look at what that is. We're subtracting that. We're subtracting that from mg. So the normal force is going to be less than mg, so you're going to feel a little bit lighter. So this is why you feel a little bit lighter on the scale, because you're subtracting that away. As usual, we're going to say g is about 10. And if I put my little approximate sign, I can do anything I want. So this is going to be 1,000 newtons minus 4 times 100. So minus 400 newtons. So this is going to be 600 newtons, right? Significantly less. You weigh less when you're going down. Very cool. Here's a couple of things to notice. So this was a really simple example, but a couple of things to notice. What if A was g? In other words, what if you're accelerating down as fast as free fall? What if you're free falling, right? if the, heaven forbid, cable snaps in the elevator, down you go. So on the way down, what you'll notice is, I mean, aside from the terror, what you would notice is if A is G, look at this expression. That's 0, right? So this is a point we'll be making a little bit later. Free-falling things have 0 normal force. You would come off the scale. You're floating, right? You would be apparently weightless. And it's not like there's no gravity, right? That's why you're falling really fast. But rather, it's that everything is falling at the same rate. The scale, the elevator, you inside. So the normal force, the contact force between you and the scale is going to be 0. So you would feel weightless as you fall. And as we'll see later, that's why astronauts feel weightless in orbit. Not because there's no gravity there, but because they're falling. They're constantly falling around the Earth. They're just going fast enough sideways so they don't crash into it. We'll see that later. Okay, so free falling means n is 0. So this is apparent weightlessness. Very cool. What if we're accelerating up? Make sure this works. If we're going up, then A is positive. And then what I would do, if A is up, then I would change that to be a plus sign. That would be plus MA. So this would be mg plus MA. So the normal force would be more than your regular weight, right? You would feel heavier by the same amount. So if you're going up at 4 meters per second, then you would feel like you weigh 1,400 newtons instead of 600. Okay, so that kind of lays the groundwork for our vocabulary and where we're going with this in terms of apparent weight in more complicated examples, which are coming up.